so be warned. Good evening and welcome to this talk entitled Bringing a 21st Century Perspective to Steam Loco Engineering. It's been given by Alex Powell, who's a mechanical engineer working in the Signals and Telecommunications Department of Network Rail and is a committee member of the Advanced Steam Traction Trust set up to promote the various aspects of modern steam. So I will hand over to Alex.
Good evening. Hope you can all hear me clearly. So I'm going to start the talk by having a little bit of an introduction about how we got to modern steam, because it helps clear up some of the things I'm going to talk about. In the UK, the final UK steam design was in 1954, and the final locomotive was constructed in 1960. The top is the final locomotive design, and the bottom picture is the final locomotive constructed. In the UK, a lot of locomotives right up to the end were designed by iteration, small changes, small improvements, and were designed by rule of thumb. There wasn't any real kind of thermodynamic design built into them, despite the fact they are, in essence, a heat engine. Although there were some exceptions, Gresley on the LNER and Bullied on the Southern did adapt elements into their design. And the top picture, the Loco, could have been world-beating had it not been poorly constructed. Overseas, you had people like Chapelon in France, who designed the 242A1, which is the top picture here, which was capable of 4,200 drawbar horsepower. And I'll go into a bit more detail about that when I talk about Chapelon himself. You had the New York Central Niagaras, which was the bottom right picture, which in a fairly balanced study in the late 1940s were equivalent to diesel and electric at the time. And it was a very close call between which motive power the New York Central Company picked. The New Norfolk and Western J was a marvel of mechanical efficiency. They were capable of 16,000 miles a month. They have roller bearings throughout, and mechanical stoking, mechanical advantages on every level. And they were oiled in, they had dedicated lubrication sheds, so everything was done in a white tiled shed with complete cleanliness to keep them as efficient as possible. And also, just to clear this up, there's a few definitions I like to go to. First generation steam, so is any locomotive designed up to 1960. So all the locos I've talked about just now are first generation. Second generation steam, which are new designs incorporating everything up to modern design, standard knowledge. So a lot of what we're going to be talking about in this talk is second generation. And third generation is totally new formats requiring considerable research and development. So that would be things with re-superheating and advanced compounding and things like that, which it probably will never be developed now, but it's still a definition that you can target for. So post 1960, or the advancements that were developed kind of after steam finished in the UK to a certain extent were Chapelon. So he's the father of basic modern steam. He created the early principles of it, which is internal streamlining, large front end steam passages to not limit the flow of gases, improved exhaust, which is his exhaust is the bottom left hand diagram there, which is a multiple jet exhaust, and compounding, where the steam is used more than once. So most steam locomotives, it's simply used once and then exhausted up the chimney. In France, it was very common to have steam used more than once. So 242A1, which is the top picture, was a compound locomotive with a high pressure cylinder in the middle and two low pressures on the outside. Because he was trained differently to how locomotive engineers traditionally were, he was pioneered the locomotive as a thermodynamic machine, and it had to be a balance of the entire system. And unfortunately, a lot of his work was damaged for political reasons, because the locomotives he was designing were more powerful than the electric locomotives that the French government had just bought. So there were political reasons specifically around his non-resistance during the war, as in he wasn't a collaborator, but he didn't resist either. So they prevented him from holding a high office after the war, which meant that a lot of his work, which included proposing steam locomotives built up to 1980 and then withdrawn in 2010, when electric locomotives would have completely superseded them. Porta, who is a basis of what a lot of the work I'm going to talk about is come from, was Chapelon's protege. He created possibly the most thermally efficient steam locomotive ever, which is the Argentina, which is the top photo, which was capable of a thermal efficiency of 13%, which I know sounds low, but is in steam locomotive terms is very good. Which was also capable of 2,000-ton freight trains in Argentina on a meter gauge, which is quite impressive. He also did a lot of work on the Rio Turbio coal railway in Patagonia, which with these 210-2 locomotives, as you can see in the picture, with a huge train, which were 1,700 tons, but they were all on 750mm gauge track. And they were capable of 500 drawbar horsepower and 12,000 kilometers a month, with virtually no maintenance required. And on those locomotives, he developed quite a lot of his key improvements, including his own exhaust, which is a LEMPOR, which is based on the MEng principle. The gas producer combustion system, which is a system where common in industrial boilers, where you have a very thick fire bed and a lot of the heat is generated by gaseous combustion above the bed, and you inject steam underneath the fire bed to keep it cool, because in coal you get ash fusion, which we call clinker, which causes prevents good combustion in the firebox and poor drafting because it blocks the airflow. So in a steam locomotive, you have air inlets above the fire and steam injected below the fire to allow that to happen. And he was also very influential in water treatment improvements. He basically applied modern power station water treatment techniques to the point where the boilers of the Rio Turbio locomotives never needed to be washed out. They would be inspected, but they wouldn't be washed out to clear the scale, which normally on a steam locomotive, you need to wash the boiler out every 28 days in steam, sometimes longer, depending on your water treatment. Wardale he applied Porta and Chapelon in South Africa. He almost managed to keep steam in South Africa going in the 1980s. He, on the top picture in the top locomotive, was a 18% increase in drawbar horsepower by applying gas producer combustion and the double LEMPOR exhaust. It also meant that on a standard service, he would do roughly 13 to 90% coal saving and 10% water saving. And in the bottom loco, it was a 37% more drawbar horsepower and a 60% coal saving and a 45% water saving. And both of them had improved reliability due to the improvements. The Red Devil, the lower locomotive, in the picture in the lower picture, was also fitted with feed water heating and mechanical stoking roller bearings throughout, although it was built with those. Completely redesign of the front end, and was a true marvel of a locomotive. Unfortunately, again, for political reasons, it was stopped. He also then went and worked in America to try and develop a coal locomotive during the oil crisis in the 70s and 80s, and finally in China in the late 1980s, because they were still building steam locomotives, although a lot of his work was not applied there. And then after that, he wrote a book, which is often considered the modern steam Bible, called The Red Devil and Other Tales from the Age of Steam, where he documented his work. It's quite a technical book, but it's really worth a read if you can find a copy. And at the end of it, he proposed the 5AT, which he then completed the calculations for. Roger Waller worked with Wardale in South Africa at the end, and then when he returned to his native Switzerland, he developed modern rack locomotives for tourist railways, which incorporated light oil firing. So it's basically diesel, uses diesel as a fuel, one-man operation, and these designs replaced diesels in service and practically run most of the railways they're on. He also developed a boiler preheating system where the boiler is kept electrically warm overnight with an external pump that then allows the driver to just turn up, turn the burner on, and away you go. He gave a lecture in 2003 to the IMechE about that. The 5AT project, which is what the AST came out of, was proposed in Wardle's book in 1998. It was set up in 2002 as a group. Design calculations were required, feasibility study and early design work was completed. It's based off the dimensions of the BR5MT locomotive. So you can see in the diagram, it's the same cylinder bore and size, wheel diameter and locomotive length, because that allowed for a longer tender, and also it was quite a common size of locomotive in the UK. So a longer tender would still fit on all modern UK turntables. So it could be used for charter and cruise trains. It was going to have a 125 mile an hour max design speed, and then would operate normally at 112 miles an hour. So it had the goal was to have a high power to weight ratio. It would have been equivalent to class 37 and 5 coaches when it was hauling 12 coaches, and a class 47 hauling 7 coaches when the locomotive was hauling 10 coaches. It was going to targeted efficiency of 14%, which is quite good for a steam locomotive, and that would have been at its maximum power. So there was potential that it could have got higher. It would have had a maximum horsepower of between 2,500 and 3,500, and its range in standard conditions would have been 580 miles on fuel and 385 miles on water, which is longer than any charter or cruise train operating today. And because it would have had roller bearings throughout and all the modern innovations from all disciplines that had been seen across the world, it would have had a very high reliability and low maintenance. And the goal was to have a fleet of 10 so you could have standardized parts. The fundamental design calculations were completed in 2005. It was David Wardle did the calculations the traditional way by hand to prove that it would have been possible in the 1950s. So it's 556 pages of calculations, specifications and diagrams, and it proved that the performance was possible. Early design work was based off those calculations and performance targets using modern CAD techniques. It took the best aspects from previous designs, and there was innovations in FEA done where possible. The feasibility study was completed and circulated in 2010. It basically set out a plan for a fleet of 5AT locomotives operating trains, and based off what would be required from the fundamental design calculations. It also set up how a team of engineers and a company would be set up to design and run the locomotives. Specified that roughly 11 million was needed. Unfortunately, due to when it was proposed, it failed to raise the capital due to the financial crisis, and the project was closed by the group in 2012. And then the Advanced Steam Traction Trust was formed from the 5AT group to preserve its knowledge and to keep the work they had done going. So the idea was to continue steam locomotive development for heritage and mainline use, because it is a huge market in the tourism world today. It's basically similar to the old Institution of Locomotive Engineers, which is now the railway division of the IMechE. We held an annual conference and we publish literature to do with modern steam. We've also undertaken quite a lot of projects, including a study on the new build clan locomotive that's being built, an S160 exhaust design. We've done a lot of performance monitoring and testing, a work on biofuels and revolution, which I will go into much more detail on later on. So this is an exhaust design for an S160 locomotive. So there's quite a few of these in the heritage market at the moment, including one that's being converted to oil firing on the Northfield Moors. It's basically applying all of the research that Porta, Wardale did in an exhaust design, and it could be fitted to any S160 locomotive. So full design and testing with all the patterns and manufacturing involved in that. Just go through. So there's the multiple jet blast pipe, and then in situ in the locomotive with all the castings and patterns that were required. Then with the clan, we were approached by them, I think it was in 2014, to try and improve the performance so that it would run successfully on the main line, which is one of their goals. This would improve the performance from a class 6 to a class 7, that's power classification, and improve the reliability, because the clans were a bit black sheep in their day. They weren't very well liked and didn't perform particularly well. So the trust did a lot of design work, which increased, recommended increasing the boiler pressure to 250 psi, fitting a single LEMPOR exhaust, removing stress raisers from the frames and other design improvements around the framing, fitting lightweight piston valves and narrow rings, which is a Porta development, which basically uses diesel technology, so very lightweight valves and very narrow rings, as in diesel engines. Improving the lubrication, so that's including fitting it directly into the cylinders rather than atomizing it as is traditional in the UK, and then undergrate steam to limit clinker, so it's kind of a half gas producer combustion system. And elements of the work, specifically the removing of the stress raisers and frame design improvements, could be fitted to other BR standard locomotives in preservation. Performance monitoring. So this was traditionally known as indicating, and in the bottom picture is how it was done in British Rail days and earlier. And a man would have to stand inside that indicator shelter on the front of the locomotive while it ran along at 80 miles an hour, which obviously wouldn't be okay in the modern world. So this uses modern technology, so pressure transducers, temperature sensors, and similar to, and position sensors to give an accurate reading of the indications of the locomotive, using a bog standard pico logger that comes through from any kind of lab environment. It can be used to diagnose faults, check performance and efficiency values. So we've used it when testing exhausts and the biofuels, and then, as I said, it's used for monitoring during fuel trials. And the trace there is a pressure transducer from the smoke box vacuum to check how the exhaust is performing. So this is something we've noticed, that in sometimes the vacuum actually goes to a pressure, which means that the fire will be blown back into the cab, which can be an issue. It also helps us diagnose a fault on a S160 we were testing. Biofuel testing, this has become quite relevant recently. So as I say, it started in 2012, but from 2021, domestic coal production in the UK ceased. So it became very important that we find a biofuel that was suitable for UK use. Through the HRA, we've had qualitative responses from a lot of railways of these manufactured fuels. And then there's been quantitative testing on the Bure Valley Railway, which is a 15-inch gauge railway, and the standard gauge Keighley and Worth Valley Railway. The two top pictures are the Keighley and Worth Valley test. So that's a biofuel ovoid, which is anthracite and olive husks crushed together with a binder. And then there's me doing water measurements to check how the performance of the locomotive was going, to see how well it was performing with the fuel. And then there's a rape oil seed cake fuel. So when rapeseed oil is created, there's a lot of wastage which can be crushed into a cake, which can be made to a fuel. These are all fuels that are available in the domestic market for home heating. So they have issues mainly around storage and friability, so they become sparks that get thrown out. The works reached a stable point. They're used a lot by a lot of railways, but they're quite often mixed with other coal, standard, like normal mined coal. So because on their own, they're not quite as good. And from personal experience, they wouldn't survive on a use on a mainline rail tour. So there's further work needed, but that requires investment and time and research, which we will hopefully be conducting. And finally, the Revolution project. So this is our main project at the moment, which is kind of a 5AT, but without the really advanced developments. It's basically a new design for tourist routes and heritage railways, where even the youngest steam locos that are running those services are 60 years old now. So it's the idea would reduce the cost of operation, it would increase reliability and reduce cost of servicing and maintenance and overhaul. And by doing that, it's basically keep it as a Stevensonian layout, because when people come to a heritage railway, they want to see a steam loco that goes chuff with rods that go around on the outside. But it needs to embrace best practice, so as much as we can from the 5AT and others, and modern materials, parts and manufacturing. The idea would be high efficiency, high reliability by having roller element bearings in lots of places, because most steam locomotives are total loss lubrication and exposed sliding bearings. It would need to be very simple, high level of standardization. So the idea is that you have a base locomotive and then you can dress it up how you want to. And therefore you could have a fleet of locomotives that might all look different, but you could have standard parts that you can buy off the shelf and replace the ones that you could that were broken on your locomotive. So therefore it reduces the cost of ownership and reduces maintenance costs. And the idea is that you could run this during the end of the season, when you need a low cost locomotive to keep the money coming in and keep the services running at make as much profit as possible while keeping the services running. So as I said, basic 260 chassis, which is the wheeler element. So there's 2 wheels at the front, 6 driving wheels. The boiler would be standard. The cylinders in motion would all be the same. The wheels and running gear would all be the same. You could alter the specification by changing the cylinder bore, the ballasting, so you would add weight to it to make sure that it had more adhesion, and then drafting, by changing the exhaust, you could make a more powerful locomotive, and it would be adaptable to as many configurations as possible. So you would have both tender and tank variants. So these are some of the tender variants. So basically it could be made to look like any kind of traditional British locomotive by changing what was the cab looked like, the cladding and stuff like that. And then you could also make it look like a tank locomotive by having a separate bolt-on frame on the back with an extra set of wheels to carry the cab and bunker. So the heritage movement is very, very resistant to change. Heritage is in its name, so they're quite resistant to new things. So it was decided that to prove the concept, a 10¼ inch gauge locomotive would be built, because that demonstrates the locomotive and it's also cost effective. 15-inch gauge would be ideal, but the cost difference between a 10¼ inch and a 15-inch gauge is about 3 times. So a 10¼ inch is the best gauge, and it also allows results that will scale up. It's also It's not a scale model, it's just a smaller revolution locomotive. And the fact that we're building it allows us to have a loco to test designs and ideas on without affecting other owners' locos and Heritage Railway services. Because when we have done this work, actual access to testing has been really, really difficult. We only managed to test the exhaust on the S160 due to the railway running a test service, and testing the biofuels involved running services in the off season, which cost the railway a lot of money, which they didn't recoup. So allowing us to test on our own locomotive is very key. So the specification is to start a fully laden train on a 1 in 40 gradient. So it gives the adhesion based on the train resistance of 3,200 newtons. So it's roughly needs 400 kilograms per driving axle. And it needs to be able to maintain a line speed of 10 miles an hour on a 1 in 60 gradient, which defines the steaming requirements and attractive power, which is 10 kilowatts. And then from that, a driving wheel diameter of 330 mil or 13 inches, which is standard for the Stapleford miniature railway that we're planning to run on. Stroke of 150 millimeters, which is the longest stroke that permits the big end bearing clearing the ground. Because of design elements, you need to think about how clearance you have on the track. The bore of 85 millimeters was got to after a great deal of messing about with the steaming capabilities, and the boiler pressure of 200 psi was picked because it's the max practical level that you can go to in 10 1/4 without getting too complicated, and it's quite a common pressure, so therefore it's quite easy to design and get a boiler certified at that pressure. It also allows us to produce the power required. And basically the size of the loco would be roughly a continental 1/5 scale, which was what was required to get the power output. When we scale it up, it will fit the British loading gauge. So all that data was put into a spreadsheet developed by the guy who proposed it, Jamie Keat, which showed the required steam pressure in the steam chest to create the power, which is 85 millimeter, which gave the 85 millimeter bore at the 75% cutoff, which is basically how a gear works in a steam locomotive. So that's 75% of the piston stroke has steam coming in, and you can see that they're trying to make sure that there was a steady tractive effort on the driving wheels. And then also through that spreadsheet, it produced a steam consumption value which was needed for the 10 kilowatt at 10 miles an hour with 350 degrees C of superheat. So that requires 0.02844 kilograms a second of steam, or 226 pounds an hour at 45% cutoff. But this assumes a superheat of 350 degrees C, which is our target, no leaks, no condensation, and no thermal losses. So this is going to be quite a hard target to hit, but we hope we've got there. One key element of Revolution's design is its frames. So Jamie was an engineer in Derby at the Church Lane at the start of his career, and he's also had to deal with a lot of frame cracking in the heritage movement, which are quite often due to poor alignment and spring failures. So there's also total loss lubrication with exposed bearings on the horn guides, which are where the axle boxes fit. And you can see a diagram of how cracking, or diagram on the right of how cracking spreads inside a locomotive's frames. And that the photo on the left shows the kind of exacting schedule for each locomotive that you would need. So they would need to be ground individually to measurements. And this is a diagram from Doncaster Works on how they optically aligned all the frames to make sure that they didn't get as much wear. This was peak 1950s and 1960s technology and worked brilliantly, but the amount of effort that you had to do to each locomotive and each axle box was huge. So we're aiming to get rid of this. The idea is that there's simple direct load paths, so there's beams between which basically directly connect the cylinder forces to the drawbar and keep the bearing centers the same. So you can see in the top picture how that would look ideally, and then on the bottom picture is how it's ended up. And it removes the complexity of alignment, and it's accurate, keeps the accuracy at the component level, which is key to standardization. And then on top of that, there would be a simple traditional plate frame for mounting the components. There's no traction forces through it, so it's completely unstressed, and it's all completely sprung, which is very important and is not common in steam locomotives. You can see where the cylinders would mount at the front. There's a fitting just behind where the traction forces go into the beams, and that allows the forces to be directly transferred into the spring beams. The axle boxes are going to be double taper rollers with fully sealed with contact shaft seals. One of the key things about Revolution is it has rolling element bearings wherever possible. They're retained by the axle and clamped with tie bolts, and there's around them, built into the spring beam, there is a spherical elastomer spring which gives primary suspension, which we think is a first in steam locomotive technology. And then the springs, there's a real issue with leaf springs and coil springs in steam locomotive use. They're a very difficult component to maintain. So going with modern Shore elastomer springs designed by Jamie. So it's a V spring with a 75% inclination, and then the actual spring body is adjusted depending on how much load needs to be supported through it. And we've gone through a full FEA validation on these, and they are going to work as designed. Then the front pony assembly. So this is the guiding axle at the front, so it has no traction forces through it, but it guides the frames. It's a simple bolt-on assembly, so it's modular. It simply bolts onto the sprung frame with a Cannon axle box with roller bearings in it, and it has a load adjustment that we can adjust depending on testing and forces, whether the locomotive requires more guidance through the load. And there is also, depending on testing, we can have designed in the ability to add side springing and lateral damping if necessary. One of the things that has developed from modern steam is the removal of the traditional spoked wheel, which are prone to cracking in the spokes. Disc wheels are stiffer and stronger for the same weight, so we chose disc wheels which we had cast and then machined out the back depending on the reciprocating mass for each wheel. And then the cylinder design was very key, so they're outside admission, so that the pipe, as you can see in the top right hand corner, is part of the steam chest, which allows as much steam chest volume as possible, which is a key for a good steaming locomotive. You need as much space and volume as possible for the steam to flow into. We looked at having them fabricated or cast using a 3D printed pattern. After much deliberation over multiple years, a welded fabrication was chosen. So rather than the 3D printed pattern on the left, we chose the welded fabrication and the diagram in the center, which has various parts welded together on two base flanges. And here's a section through to show the different components. It allows Accuracy, self-jigging was designed in, so the parts fit into the two purple upright sections and allow the weld to go around them, so that there's no need for jigging of the actual cylinder itself while it's welded. It keeps the important features at a component level to make sure that accuracy is maintained. It also allows much more ability to machine the internal spaces, which allows much more complex pattern and geometry of the passages, and also allows us to fit steam jacketing, which is where you apply steam to the outside of the cylinder in a space that keeps the cylinders warm, which means that you don't have what's called condensation losses, where your steam is admitted and then immediately condenses, because you're basically putting hot steam into a very cold metal environment, and that increases efficiency. And the welded fabrication significantly reduced the cost. So the top picture is the kit of fully machined parts for both cylinders. So you've got the two end valve chests, the central beams, which everything's mounted to, the central valve chest with the actuator space, and the cylinder bore. And then once they were welded, they have been stress relieved to make sure that they didn't bend out of shape. And then final boring was done post welding, and then there is a cylinder liner and a valve liner that are inserted into them. Once again, the connecting and coupling rods are roller bearings. They are deep groove ball bearings, and the rods are manufactured from aluminium to reduce the reciprocating mass, and have been fully tested to show that they wouldn't fail under use, which they won't. If the locomotive was scaled up, aluminium wouldn't be used, but in this situation, they were applicable. Another element that came from the 5AT and has been applied elsewhere by members of the team was a roller sliding bearing arrangement. So traditionally, a slide bar on a steam locomotive is just a sliding bearing with bronzes. The rolling element slide bar allows reduced friction, less wear. It's symmetrical, so it can be fitted to either side. So it's not a handed part, which traditionally these are. And the V rollers allow perfect alignment, which again is quite key in reducing wear on steam locomotive piston rings and valve rings. The valve gear, which is what allows steam admission into the cylinder, has been designed by Richard Colby, who's master at this. Is a modular subassembly. So again, it's not handed. You could literally bolt this onto either side of the locomotive. It doesn't matter. It's machined mounts, slide bar support. So it supports the slide bar, so the whole thing can be bolted on or taken off for maintenance, depending on, and then replaced with a different one. So that it's modular, and therefore it's can be replaced by like for like part, keeping maintenance down. And it's fitted with needle rollers throughout to keep the roller bearing and wear down, so that the whole locomotive is on roller bearings. The boiler design, we are indebted to Martin Johnson, our member for this, who has developed a boiler design spreadsheet that has been proven in service. Martin was a chap who worked for Babcock and Wilcox. And it's basically, we're optimizing the design based around performance and the ease of maintenance. So the target is to meet the steam consumption that we require and the 350 degrees C of superheat. Currently, the design is 4 superheater flues with 2 elements in each superheater flue, with auxiliary supply using the superheated steam. So we have what's called a regulator valve. So the steam is always in the superheater elements, which are passed through the larger tubes in the boiler. And then because we have a dry side regulator, we have an emergency steam shut off if one of the superheater elements fails, although having a dry side regulator means that the superheater elements are kept cool and therefore less likely to fail or burn fail. The ash pan has been designed as combining the best gas producer combustion system and 10 1/4 inch practice. So the ash pan has been designed easy to empty out the ash in a 10 1/4 inch gauge environment. Also has dampers fitted and under fire steam jets. The Loco is too small to require side inlets into the boiler because of all the required steam for a gas producer system is able to enter through the firebox door. The front end design is obviously Revolution is going to be an exhaust test bed for the trust. So we're going to start with a well-designed simple exhaust, not fit it with a LEMPOR, and then as we go through, we're going to design LEMPORs to see, and then we can compare the performance with a standard exhaust to a LEMPOR exhaust to truly prove how good a LEMPOR exhaust actually is. We're planning to change the exhaust regularly, so the smokebox is designed with a easily removable section, so it will be very easy to change the chimney and exhaust system on the inside. The exhaust system and chimney are bolted to the top of the smokebox normally, so they will be very easy to lift them out and replace them with a completely different one. The pipework in the smokebox has been designed for the best flowing and largest steam circuit possible, which is a Chapelon principle. So you've got a smoothest curve so that there's no restrictions of flow and losses in the tubes to the cylinder, so you get as much power out of the steam that you've produced as possible. As you can see the sweeping curves in the lower picture. The tender is a larger water tank as possible with design for one person. It's also been designed with the ability to try other fuels. So again, Revolution is a test bed locomotive, so we've designed it with the ability to fit solid fuels and also potentially for oil fueling or gas even. It's based on an unusual construction method, so we've been following hydraulic tank design for that, which is quite unusual for a steam locomotive. And then obviously there's the base frame and bogies underneath. The bogies are using the same principles as the locomotive, where there's a spring beam and an elastomer spring to allow smooth ride. And it uses the same design of spring. So again, a good standardization of part. So the same spring design is used on the locomotive and the tender. You just need to adjust the type of rubber used, which gives the length of the spring to give a different springing load. And so far we've got a rolling chassis. You can see here that this is just the spring beams, so there's no framing on top of it in this picture. We've also got the sprockets there are fitted for two reasons. One, if we want to do a dynamometer test bed, we are planning to use chains to connect it up to a dynamometer, basically a generator to check the power output, because there are issues with the rolling road kind of test bed that were discovered after a lot of them were built in the 1940s and 50s. And in that picture, you can also see the disc brakes on the locomotive. So this locomotive is going to have disc brakes to improve its braking performance. And then that's the running chassis with the spring beams mounted onto the sprung frame with the pony truck bolted onto the assembly in the front. And we did some testing with the locomotive at the Stapleford Miniature Railway in September 2023, sorry, where we ballasted up the loco to take how much weight it would be on the springs, and then drove it round the track hauled by a diesel locomotive. and the results were pretty good. So I've got a quick video of the locomotive running on that test. Hope. Oh. Oh. I apologize, can't play the video. Hopefully I'll be able to play that at another time. This shows the tender construction. You can see there the spring beams with the elastomer springs, which are exactly the same as on the main frames of the locomotive. And then the tender tank with the baffles fitted to the top of the tender, which allows for a change in tender design quite easily, which is quite key for our different testing of different fuels. And then there's the tender complete and painted, and it went on display at the Greatest Gathering in August last year, which generated quite a lot of interest. And then just to close, I'd like to show some advantages in being a member of the ASTT. So there are member-only pages of our website. You've got access to the archives, which include all the conference presentations that have been given over our many conferences. You get a discount on our publications and opportunities to learn about steam technology, opportunities to contribute to Revolution and other projects that we're working on, so that steam locomotives can continue to operate on both heritage and mainline. And obviously opportunities to meet and network with other members who are experts in their field in steam locomotive engineering. We have a full range of publications, so you can purchase the 5AT Fundamental Design Calculations and its feasibility study. They're quite heavy going, but they're very interesting. Porta was a prolific publisher of papers, so the Trust has been working over quite a number of years to have them published in volumes 1 to 5, where basically details all of his work, some of his ideas, and the idea is that if they're published, they're available to people to try and apply to steam locomotives. We also have a compendium on him in volumes 1 and 2 that show as a collection of papers about him, not just written by him. It gives a kind of history of his life that we conducted for his 100th anniversary of his birth. And then we also have the Lynn Design Specification and Calculations, which is the work done by Ian Gaylor in designing a new steam locomotive for the Linton and Barnstable Railway in Dorset, Devon, based on the original locomotives that ran there, but brought up to modern steam design. So it has a modern exhaust and gas producer combustion system fitted, but not in use currently. And any questions? Hope you all enjoyed the talk.
Well, thank you very much, Alex. That was really interesting. As I said at the start, if you have a question, can you please write it into the chat, and then we'll go through them as they come up. It always takes a little time. So, Alex, when do you think that you will actually have this locomotive operating? When will it run for the first time?
It's a few years away at the moment, because unfortunately we've kind of got to the point where we have to build the boiler now, and that's quite an expensive. It's the most expensive part, basically, and we're just finalising the design. So I would say optimistically 3 years, but hopefully sooner than that.
Okay. Right. First question has appeared. Is it planned to test biofuels on Revolution?
Yes. Yeah.
Bio-oils. Sorry, bio-oil.
Ideally, yes, it would require some extra design work. The idea is to run it on coal to start with, to create a baseline to compare things to. The tender, as I said, the tender is designed to be able to fit it with oil tanks so that we could run an oil fuel system on it. We have also potentially thought about running it on a gas fuel as well. Yeah.
Okay, well, there's a follow-up. I'm taking questions slightly out of order. Have you identified particular oils such as raw sunflower oil?
We haven't looked into it that much yet. Most of the work the trust has done on fuels has been based on solid fuels, because in the UK, oil burning on steam locomotives was not common. It was tried, but not very successfully. So it's an area of research that will need some work done. The research we've done is on solid fuels, because that's what the Heritage Railway movement needed when the Fosse Fan colliery in Merthyr Tydfil was closed in 2021, and then it reopened and closed again. Basically, the loss of domestic fuel supply meant that a biofuel was necessary to be developed, and there was a lot of research done at that time. Oil firing is being tried in the UK. The North York Moors are going to run theirs on oil so that they can, as a reduction for fire risk. So they are in the middle of converting a locomotive for that, and I think they are planning to run that on vegetable oil. I might be wrong, but yeah. So there are routes to that.
Okay, thank you. Have you, or do you intend to do testing at component level, for instance, on accelerated aging tests on the springs?
We don't plan to at the moment. I would imagine that once the concept has been proven and the heritage movement has decided that they want the design, because that's the key. Revolution is designed to prove the concept of a steam locomotive that has the base locomotive that could be dressed up to look whatever the heritage railways want. Once the concept has been proven and there is actually interest on a full scale locomotive being built, the extended testing, like age testing on components, would probably be part of the design phase of the actual locomotive, the full standard gauge locomotive.
Okay, both Chapelon and Porta were big advocates of compounding. Is there still resistance to it here in the UK?
Yes and no. There were some railways that were very good at it. The Midland Railway had a very good compound, and there is one of those preserved. Again, because everything was designed by a rule of thumb in the UK, compounding was never particularly successful. Whereas there were drivers for it in France, which were based around there was a fixed speed limit, so they had to be as efficient as possible at that speed. So they were very driven by efficiency, which meant that compounding developed. There is still resistance in the heritage movement to it, mainly because there are no compound locomotives running at the moment. And the reason the Revolution isn't a compound locomotive is that it needs to be simple to get through that initial resistance of the heritage movement. There was some discussion when the 5AT was proposed as to whether it would have compounding, and again, in the end, for simplicity, it was decided that a simple locomotive would be better. But there could be opportunities for compounding in the future.
Okay. Have you links with the Prince of Wales group at Darlington?
We have some members who are also members of the Prince of Wales group. They haven't approached us for any work or anything like that. So we're connected through things like the Heritage Railway Association and things like that. The cylinder design of Revolution was kind of influenced by their decision to fabricate their cylinder as well. So there are some connections in that sense, but in terms of an actual discussion between the two groups, other than we visited them at our conference this year, not really.
Okay. Any plans to use CFD, computational fluid dynamics simulations, particularly on the exhaust systems?
Yes, there are plans to do CFD simulations on the exhausts. Yes, and I'm fairly certain that Martin Johnson, the chap who developed the boiler design spreadsheet that we've been using, has been looking at exhausts from basics of fluid dynamics, and has written several articles about it, and also in the most recent volume of Porter's papers did a large amount of work on his LEMPOR theory paper, which specifies specifies the theory of how a LEMPOR exhaust works. So there is a lot of opportunity there to do computational fluid dynamics on that front.
Okay. Engineers are also drivers in France for the compounds, if I'm not wrong. They had special training and called mechanician. I guess this is the drivers like the compounds.
Yes. So in France, it was very different to the UK. They were almost engineers in their own sense, whereas in the UK, the drivers they weren't engineers, but the UK was actually better than a lot of other places in the world in that they were taught to be very efficient, and little and often firing, which is the key to efficiency with non-gas producer combustion systems, was taught very well in the UK. So the French system was very different and potentially better because they were engineers in their own right. They understood how compounding worked and could therefore drive it more effectively.
Okay, thank you. What are your thoughts, plans for lubrication on the cylinders of Revolution?
It's going to be a standard mechanical lubrication, but we're planning to directly admit the oil to the cylinders as close as possible, as close as we possibly can, and we're going to be applying as much of the lubrication techniques that Porta specified as possible, because they are key to improving wear and piston life. So it's direct admission lubrication.
Okay. Have steam turbines ever been considered for use in trains, or is this the third generation that you mentioned at the start of your talk?
Steam turbines have been used. There was a very famous one in the 1930s and 40s called the turbomotive. It's quite unusual, and it would have been very successful had the Second World War not happened. It would definitely be considered a third generation because that would require much more research. And that was a direct geared turbine, so it was still a mechanical, and there might be some suggestion that an electric drive would be better.
Okay. I've got a couple of, I think there are more comments that you had a French member of the audience, so to be careful on what you said, but I think you were quite complimentary about what the French had done, so no problem with that. Are there any further questions? In which case, let me thank you very much, Alex. This is not an area that I'm familiar with at all, and I found it really interesting and actually really very impressed at how far you had taken this work and the thoroughness of some of your analysis. We are getting one more question. Sorry to comment. GE, General Electric, did the steam turbine in the 1930s.
Yeah, there were definite applications of steam turbines, but they were kind of, the development of them was kind of stopped by the Second World War, and then the minute diesels came around and electrics, that kind of, they stopped research into it.
Okay. Right, sorry, that was a by the by. Thank you very much, Alex. We had a really good audience here tonight who've largely stayed on for the questions. So thank you very much. Thank you everyone for attending, and I'll try and notify everyone when the recording is available.
The presentation should be available on our website shortly, as in the slides.
Okay, and I'll send that link out to all of the information. Okay, thanks very much, Pete, everyone.